Hey, it's Mr. Armin, and this is section 5.4 on our how-to series, and we are how-toing microcentrifuges in this video podcast. Alright, so everything you want to know about microcentrifuges and how to operate one, what the do's and don'ts are, and maybe what is a microcentrifuge. Maybe we should start off with that. Alright, so objectives from this is things that you're supposed to take away here are, first, how does this microcentrifuge work? What does it do? What's it supposed to do? How does this work? And then secondly, how to operate a microcentrifuge. You could really mess one up if you're not sure how to use it. And so we're going to go through the details on how to operate a microcentrifuge, and that way you can do one. All right, so let's start off. Well, some of the questions, like I said before, that we're going to want to know first off is, what is a microcentrifuge? So we'll talk about what that is and how do we operate one next. All right, so what are some of the things we should do with the microcentrifuge versus some of the things we should not do, and ultimately, how does this really work? What's the magic behind it, right? Is there any magic behind this at all? All right, so let's talk about microcentrifuges. So what is a microcentrifuge? Well, a microcentrifuge is a small centrifuge, obviously, and it's also called a microfuge for short. It is an instrument that's used to kind of separate out these chemicals or substances inside of a solution by a process known as sedimentation. Think of, maybe you were at the beach and kicked up a bunch of sand, and the sand was just kind of brushing up against your legs, and then after a while that sand all seems to settle down to the bottom of the shore, right? So there you go. That's sedimentation, and this is essentially what's going on. I mean, there's an effect of gravity that's pushing down on your stuff in your solution. So the basis of centrifugation is the effect of gravity on these particles, on these solid-like particles in a suspension or in a solution filled with stuff that's floating around. All right. Centrifuges are going to use something known as centrifugal force. Centrifugal force is also known as a G-force, and this is going to isolate particles from their surroundings. It's going to pull them apart, and it's going to hold them together, the like particles together. And so you're going to be able to effectively separate out layers of stuff inside of your tube using centrifugal force. And I like to think of it in a way as kind of like whenever you're on a roller coaster, right? Centrifugal force is, you get to the top of this roller coaster ride, right? And it clicks all the way up to the top, and then there's that feeling of weightlessness at the very first part whenever you're looking down at the tracks below, and then all of a sudden your face is pushed to the back of the seat, right? It's like your skin is folding on itself, and you got the weird, and I wish I could show you what my face looks like because it looks pretty silly, but you got the, like, your cheeks like held back and everything, and it's just like, as you're going down the ride, right? So all this force is pushing back against you, and that is centrifugal force. This is the force due to these G forces that are pulling down on you, and it's holding you in your seat actually whenever you're doing these loops, and it's a good thing that's there. If not, it's real easy that you just slip right out and fall out of your seat if you weren't buckled in, right? We keep the buckle there just as a safety precaution. So this is the centrifugal force is going to be what holds this stuff, takes this stuff and it pushes it towards a side of this test tube. We're going to use that to separate out your stuff. So while many particles in the liquid are going to eventually settle down by gravitational force, it can sometimes take a long time, and it's more often more time than we want to spend just sitting there waiting for the particles to settle out of solution. So we use this instrument to increase the number of G's or G forces that are applied to the particles in a suspension. So it's kind of speeding up time almost in a way in which it takes so much time for these particles to settle down. It speeds up this process. Boom, all the particles, bottom of the tube. All right. And the way it does this is this process is going to separate out by gravity working on particle density. So all these particles are going to be ones that are not alike are going to have different densities, right? Obviously, ice is less dense than water is, right? It floats. But you have different densities for different particles inside of your solution, and this is a way of separating it out by the density, right? So the things on the weigh the most, the things that are the most dense, are going to be on the bottom, and the things that are the least dense are going to be on the top. So what is centrifugation? So centrifugation is going to push G forces down on the solution, and it's going to force these particles of denser particles down towards the bottom, and that thereby is going to, all the lighter particles are going to be lifted up and placed on top of that denser layer. So we're going to watch this happen. All right, so I'm going to take this test tube and I am going to place it inside of a centrifuge, and we're going to watch what happens to the particles inside of this test tube here. So I just put it on spin, and so once I put it on spin, the G forces are going to push down on those particles inside the solution. All right, and that's going to force all those particles down towards the bottom. All right, so at the very end of my spin, all the particles are going to be down at the very, very bottom of this tube, this microcentrifuge tube or PCR tube, depends on whichever one you're using. So the solid material is going to sink to the bottom of the tube, and this solid material, this collected solid material that was once mixed in the solution, is now going to be separated. And this solid at the bottom is known as the pellet. They call it the pellet or the solid phase. Oftentimes we call it the pellet. All right, so the pellet is going to be what's located at the bottom, and it's going to be that solid phase is going to be separated out from that top part, the liquid phase, which is going to be on top. All right, so there you go. So the liquid that's on top is going to be known as the liquid phase, or what we like to call the supernatant. All right, so the supernatant, super because it's going to be, well, not just because it's awesome, but it's on top, right? So this is going to be above the pellet, and so the supernatant is the liquid that is above the pellet. So there's your pellet, there at the bottom, and there's your supernatant. All right, good to know. Good to know. Keep that in mind. So how exactly does this work, this centrifugation process? All right, so how is it that we are able to get these particles down? Is there some sort of magical force that's causing these particles to shift downward? There was once a ride, I don't know if there still is or not, but there was once a ride at the fair called the Gravitron. And Epcot has a ride in Disney World similar like this. It's called Mission Space, I think it is what it's called. And basically, you are in a centrifuge, all right? And it's going to put G forces on you by spinning you around in a circle really fast, almost like a blender, right? And these G forces, you're going to feel the impacts of these G forces, and you're going to be pushed back into the chair, basically. So this centrifugal force, or G force, if you've ever taken a physics class, the one thing that they drill into your mind is this: F equals ma, right? So F, the force, equals the mass times the acceleration, right? And so if we're going to get a g-force is just any other force, right? So if it's a force, there's going to have to be two things involved. There's going to have to be a mass, and there's going to have to be an acceleration. So not just speed, but the change in speed over time. So the acceleration. All right, so force is going to equal to mass times acceleration. All right, so what's going to happen here is that we can monitor the g-forces by counting the number of cycles. And so we take a fixed point on this circle, right? And the time it takes for it to spin completely around this thing and come all the way to its original starting point, that's known as 1 revolution. All right, so that is a revolution. And so what we can do if we want to monitor how fast this thing is going, and we can track its acceleration by counting the number of revolutions that happen in a minute, right? So, you know, if it's 60 revolutions per minute, we abbreviate that with the letters RPM. So revolutions per minute is RPMs, and you might have heard of RPMs if you've ever listened to or read a automotive magazine, and it talks about transmissions and be able to accelerate, and your vehicle is able to produce so many RPMs, right? So that's revolutions per minute. So there you go. So we can monitor how much that g-force is going to be placing down on that sample by counting the number of revolutions per minute or tracking the RPMs. Okay, so the greater the number of revolutions per minute, the greater the number of g-forces, all right, that's being pulled down on our sample. So if we start off and we have a small spin, as you can see that's noted here, so a small spin proportionately is going to give a small amount of force. All right, so a little bit of force is going to be pushing down, and so you're going to speed up the gravitational process just a little bit. All right. However, if instead we use a tremendous amount of speed, all right, so we are going to ramp this thing up, and it's going to be going 90 to nothing. All right, if it's got a tremendous amount of speed and it's producing a lot of RPMs, then what you're going to notice proportionally is a great amount of force. All right, the more speed, the more force that's going to be pulling that thing towards the center. All right, and so that's what we're going to be looking at. All right, so now that you kind of understand how a centrifuge works, you're going to need to know a few things before you actually load and operate a microcentrifuge. All right, so it's a very, very delicate piece of machinery, and costs lots of money. So prior to loading a sample into a microcentrifuge, you're going to want to make sure first off, before you even close the lid or you put the tubes inside the microcentrifuge, make sure that the tube caps are tightly closed. All right, so make sure the tube caps are tightly closed. And one other thing that I like to do, make sure that you guys do, and it looks like they've done in this image here, is that, and this will kind of help with all of that, make sure that the edges of the cap, this one looks like it might be just tucked in, but the edges of that cap are pointing outward. All right, so they're pointing out towards the side, and so that way it's not causing these tubes to spin individually inside the rotor as it's moving around. Okay, so if you have that flap of the cap facing out, that tube's not going to spin, and if it spins, there's a chance that it could knock out one of the microcentrifuge tubes or PCR tubes that's inside the rotor. So let's talk about what a rotor is. Those of you that are familiar with vehicles, cars, trucks, things like that, you've probably heard of the term rotor before, and you probably know what a rotor is. In a microcentrifuge, or in a centrifuge in general, a rotor is just going to be, for us, a spinning wheel that's going to contain our samples. All right, so this is a spinning sample holder. The deal with this rotor, and just like in a vehicle, is that the rotor has to be balanced. If you're going at great speed and you don't have a balanced rotor, rotational motion, you're going to put some damage on the rotor and on the microcentrifuge. All right, some irreparable damage, which means lots of money. Okay, so we want to make sure before we run a microcentrifuge or a centrifuge that the rotor is balanced. All right, so here's the deal. You want to balance a rotor, you want to run a microcentrifuge, you got to consider three things. All right, first, you need to know and make sure that they all have equal-ish volumes. All right, equal volumes. They need to all have equal masses. Important. And probably the most important thing, they need to have equal and opposite position on the rotor. Okay, so I'm going to show you exactly what I mean here. So first thing is that you want to make sure that the volumes of the liquids are going to be the same. If you're using the same concentration of a solution, especially so, because then the masses are going to be different, right? And the masses are different, the volumes are different. It's going to be out of balance and you're going to mess up the rotor. All right, so please make sure that you have the same volume of the solution inside your tube. If you know for a fact the volumes are identical, you won't have to do the next step, which is finding the mass. All right, but say you are we're taking the class together, right? And everybody's loading their sample into the rotor. You're not going to know exactly how much liquid they put in if you didn't sit there and watch them. You know, make sure that they did it correctly. And so another way to ensure that the rotor is going to be balanced, if it's the same concentration, is that you find the mass, right? If it's the same concentration and it's the same volume, it should have the same mass. Okay, so one way we can do this, and what we will do, is we'll have a log that's set out to the side of the centrifuge. All right, and you're going to just quickly place your centrifuge tube, or microcentrifuge tube, PCR tube, whatever, on the analytical balance, and you're going to record the mass on the record. All right, and you're going to look to see if there's a large variation in the masses. All right, if you notice that the mass is different than everybody else's mass, you need to go back and check and make sure that you put enough of your sample inside your tube, or maybe you put too much sample inside your tube. And so weighing it out on a balance is going to help you in determining, make sure that you have the exact amount of sample as everybody else inside the centrifuge. All right, and so you're going to want to equal out that weight. All right, so volume and mass, and those are important things, right? But this last one is the most important. Not to say these aren't important, they are, because this can, if you don't do this, it will damage the rotor. But if you don't do the other thing right here, position, you don't do it correctly, it will certainly and very quickly and definitely damage the rotor. All right, and you're talking lots of money. All right, so position, making sure that you have a equal position, an opposite position from where these samples are located. So when balancing a rotor, make sure that you position your samples. And the way that I like to think of this is kind of like a tug of war. All right, so in the center of your centrifuge is the center of the rope, right? And on the two ends, you have the two people tugging on the rope. It's tug of war. And if it's the same mass, same volume on all sides, then you have a balance, basically, right? And so you're not going to have to worry about what happens whenever it spins, because what's happening on one side is going to be equal and opposite to the other side. And so it's going to cancel out each other. All right? But if you have too much weight on one side, that's going to cause, whenever this thing, when it's spinning, it's going to spin unevenly, especially at high speeds, very, very high speeds. You're talking somewhere around 14,000 g-forces. All right, so this is a tremendous speed that this is going to go through. And even the slightest bit off can damage the rotor. So make sure that these are positioned accordingly. All right, so I like to think of it. All right, so you have, if you have one on one side of the centrifuge, you want to make sure that at the exact opposite position that you have one on the other side. Okay, exactly in the opposite position. If it's over one to the right or one to the left, that's enough to mess up the rotor. Okay, make sure it's exactly opposite from your initial sample. If you have three of them, you can have a three-way tug-of-war right here, right? So you can have one person on this side, one on that side, and one on this side, and if they're all pulling at the exact same force, then essentially this center part is not going to move. It's balanced. All right, so you want to make sure, if you're doing an odd number like 3, that you have it in equal and opposite positions, and you can count the number of spaces in between to make sure that they are in equal and opposite positions. All right, so if there's 4 spaces in between this one and this one, you want to make sure there's 4 spaces in between that one, and then 4 spaces in between that one and that one. Okay. Now, an important thing to note is that you should never run a single sample by itself, ever. Period. All right. So if you only have one sample that you need to have centrifuged, you always run what's known as a counterweight. All right. So something that is equal volume, equal mass to the whatever it is that you have inside that sample tube. All right. So that way it counterweights or counterbalances out the initial sample. All right. So it keeps the rotor balanced. All right. So let's try practicing some centrifuge loading techniques here. All right, so if I think I'm going to take a thick pen here. If I have a load this spot right here. So if I load this position on my centrifuge, on my rotor, and I only want to run one sample. Important thing, what do I need to remember? Do you remember? I'll give you a second. So if you're just running one sample, the thing you want to remember is always use a counterweight. Counterweight. And so I'm going to denote counterweights by coloring those circles that are counterweights in orange. And then the samples will always be in black. Okay, so the orange is not a real sample. It's a counterweight. It's to keep the rotor balanced. Okay, it's equal mass, equal volume in the opposite position to satisfy this whole balancing thing. All right, so if I want to load just one sample, I'm going to have my sample tube on one side, and then I'm going to have my counterweight on the other. Now, it doesn't matter that I put it at the 12 o'clock. I could have put it at the 1 or at the 3 or whatever, and then I just have to make sure that directly across from it, I have the counterweight. All right, so let's double check and make sure that we've got that right. Yeah, there we go. Now, what if I wanted to load 2 samples, right? So I wanted to load 2 samples on this rotor. Well, I would just take out my counterweight, which is located here, and I would, in this spot, put my second sample, right? So my second sample should be equal mass, equal volume, and then I have, boom, a balanced rotor, okay? What if I wanted to load 3 samples? Take a moment to think about that. So 3 samples, I'll have to do a little bit of arranging, right? And so if I wanted to do 3 samples, I could do that. But I would have to have it to where there is an equal distance between the 3 samples that I have here. All right, so this would be a sufficient organized manner for balancing the rotor in this situation. Still, I don't like that. I would still probably put 2 on one side and then 1 with a counterweight on the other side. But that's just me. Technically, you could do this. All right. What about 4? Well, if it was 4, it'd be 2 on each side, right? So 2 on each side for 4. What about 5? You getting the idea here? You getting what's going on? So 5, you're going to have 1 or 3 on one side, and then 2 with a counterweight on the other side, much like you see here. 6, take out the counterweight. 7, you understand what's going on here, right? You got it. All right, and then 8. Okay, so a few things. You're going to have some practice on a worksheet first on how to arrange your rotor. Make sure that you understand how to do that. There's also a virtual exercise that coincides with this lesson on centrifugation. And what you're going to want to do with this is go through this lesson. At the very end of the lesson, of the interactive lesson, there is a certificate. Okay, so you put your correct first and last name at the very beginning. At the very end, once you complete it, it will give you a certificate. You will print off that certificate, and then, or you can email me that certificate, and I will print it off, and I will put that in the grade book for you for a grade. And that's basically covering all the topics that we talked about with centrifugation. Okay. So real quick, let's review what we talked about. The first thing that we said was that centrifuges are going to use something known as centrifugal force. All right, so that's going to impose this G force to isolate particles from their surroundings. And if you took sweet tea and you spun it in a centrifuge, you get the sugar back out, right? People think that the sugar is performing a chemical reaction when you put it in sweet tea. No, the sugar's still there. You just can't see it anymore. It's evenly mixed. So if you put it in a centrifuge, you're able to pull out all of that sugar that you initially put in the sweet tea. And so someone says, "Oh, you gave me sweet tea. I asked for unsweet tea." You just take it, put it in the centrifuge, and pour out the tea. And it's unsweet tea, right? Or you can just give them unsweet tea. How you want to do it? All right, so there you go, centrifugal force. So centrifugation is going to separate by the influence of gravity that's imposing on particle densities. All right, so each particle that has a different density is going to be separate from each other particle. After you've done your centrifuge, what you're going to find is that the solution is going to be separated into 2 phases, a solid phase and a liquid phase. The solid phase is known as the pellet, important to know, and the liquid phase is a supernatant. So super above, Superman, above man, like he's super powerful. So supernatant is above the pellet or solid phase. The more revolutions per minute, the faster your centrifuge is going to go. Which means the faster it's going to go, the more G-force is going to be exerted on your solution. So that means the faster this gravitational pull is going to pull down on those particles in the solution. Important to know before you start centrifuging is that the rotor must be balanced to spin the centrifuge or microcentrifuge. And remember, there was 3 key things in balancing, right? You have the volume, the mass, and the position. Position, most important, make sure that they are equal and opposite positions to balance that rotor. But you also want to make sure that the mass and volume are also the same. Okay, so that is everything that I wanted to cover with you on microcentrifuges. And you are now a microcentrifuge master if you've retained all of this information. And so I want you to check your knowledge by going through, doing the practice time review sheet, and also getting that certificate. All right, so get online to the NC Bio Network's website for the virtual lab for the centrifuge. All right, so get on there and do that and print it off and turn it in, or email me that printed copy with your name on it, so that way I can check you off the list and you will be good to go. All right, so I want to make sure everybody in the lab is going to be able to operate a centrifuge safely and that you possess the skills to perform it correctly. If you have any questions for me, you know where to find me. Monday through Friday. Alright, so I am going to head out from here, and I will see you guys soon.